From the dawn of time, we have continuously worked on ways to improve our creations. Artisans, manufacturers, scientists, and engineers have for centuries manipulated the materials they work with to produce better products. Experimentation has included changing or controlling such elements as temperature, pressure, and composition to achieve steps forward for innovation. However, for all the manipulation and control these inventors exerted over their productions, the constant pull of gravity was one element they were unable to subjugate. Gravity is a constant force and an invisible element that controls the way many of the things we use in life and work. But where scientific research is concerned, gravity can impose many restrictions. Scientific experiments involving fluids whereby components such as sedimentation, fluid density, buoyancy, and temperature differences are examined are severely limited on Earth. As sedimentation and buoyancy-driven convections are dominant on Earth and can thus hide the true behaviour by the transport mechanisms that fluid physicists are trying to better understand. This is why experiments in microgravity are ideal for fluid experimentations, as the low gravity effectively eliminates sedimentation and buoyancy issues. The Space Shuttle contains a space-based laboratory and presents scientists with a new environment in which to conduct experiments. Because the environment is in a situation of microgravity, gravity is no longer a constant force for experiments. This results in a whole new range of research opportunities available to scientists in many fields of study. Astronauts are often described to be experiencing zero gravity in space. The term, however, is technically incorrect, as even at 300 kilometers into space, gravity still exercises 90% of the attractive force it has at the Earth's surface. The concept of microgravity is a simple one. If you can imagine riding in an elevator to the top floor in a tall building, just before you reach the top, the cable breaks and the elevator begins to plummet towards the ground. As you free fall towards the concrete below, the elevator, yourself, and anything else inside are accelerating at the same rate due to the pull of gravity. Everything seems to float, and for a brief period, the effects of gravity seem to disappear until you hit the lobby floor. This is exactly what happens on the Space Shuttle. Once the shuttle reaches its orbit above Earth, it is travelling at a fast enough speed to maintain a continuous free-fall effect. This free-fall environment in turn creates the microgravity conditions that make things appear as they were floating, when in actual fact, they are falling. We experience microgravity when bouncing on trampolines, riding roller coasters, or diving off a diving board. Over 200 years ago, inventor William Watts discovered that he could produce superior musket balls by dropping molten lead from a tall tower. Since then, scientists have carried on this concept with experiments conducted in taller, more sophisticated drop towers, or in research aircraft such as NASA's KC-135 or suborbital rockets. But even with such advances in technology, periods of free fall are still limited to less than 10 minutes. On the Space Shuttle, however, scientists can experience more than 2 weeks of microgravity. The International Space Station is a more permanent microgravity research facility which can host experiments for long periods of time and can facilitate experiments into areas such as fluid physics. On Earth, liquid is considered as drops, streams, puddles, or even just the shape of the container it is occupying. In microgravity, however, liquid has completely different physical characteristics. No longer bound by the abundant gravity of Earth, surface tension reigns, allowing the liquid to form into a near-perfect sphere. It becomes a self-contained vial of liquid, free-falling with the rest of the shuttle's cargo. This fluid physics experiment on the sphere of liquid uses the drop physics model. The drop itself is suspended due to the free-falling effect. The movement is caused by sound waves, which are being used to maneuver the drop. One-of-a-kind experiments such as these give fluid physicists an opportunity to test hypotheses that were formulated on Earth.